Good afternoon, everyone. My name is Nils Jarnsland, and this is my presentation on Vaneaxial fans. A vaneaxial fan is an air-moving device with axial airflow and straightening vanes to reduce swirl created by the rotor. Vaneaxial fans are a type of axial fan, which are one of two types of industrial fans, the other being centrifugal fans. The key design difference between these two is that the centrifugal fan receives air at right angles to the intake of the fan and spins the air outwards, whereas the axial fan forces the received air to move parallel to the shaft. Benefits of axial fans are that they are lighter, have a lower operating cost, and they take up less space. As a result, use of axial fans in the low pressure range, up to 0.142 psi, is much more frequent than centrifugal fans. Axial fans are also better suited for certain plant layouts because of the straight path between the suction and discharge nozzles. This results in the axial fan becoming a round duct, whereas the centrifugal fan requires a more expensive solution to install. They also have lower pressure airflow, which means they require less power. The vaneaxial fan's name comes from the guide vanes in the fan tube that improve the efficiency of the fan by directing and straining the airflow, which minimizes turbulence and reduces noise, as shown in the figure. As a result of this, vaneaxials are typically the most energy efficient fans available and are used whenever possible. Vaneaxial fans are used for heat, smoke and fume removal, process drying, comfort and process cooling, and general ventilation. They are usually run at low speeds and moderate temperatures and also experience large changes in airflow with small changes in static pressure, and can handle large volumes of air at low pressure or free delivery, which is the condition of maximum kinetic energy. The following clip further depicts the effects of the guide vanes have on the fan's efficiency.
Fans after the impeller are carefully designed to calm the airflow, and fan efficiency is further improved. Optimized leading edges of guide vanes can help to reduce tone sound by dispersing airflow knocking on them.
So that was how the guide vanes help to further reduce noise and turbulence, as shown through the CFD model that they were using. So next up, vaneaxial fans are arranged as either a direct drive fan, where the rotor is directly attached to the motor, or are belt driven. Advantages of the direct drive are that it is more compact, has no drive losses reducing efficiency, and requires relatively little maintenance. The disadvantages are that the fan speeds are limited to the motor speed if used without a variable frequency drive, poor motor accessibility, and maximum airstream temperature of 105 degrees Fahrenheit using standard motor insulation. Belt-driven fans have the motor mounted on the fan housing out of the airstream. A belt tube provides passage of the belts from the motor to the driving pulley. Belt drive advantages include the wide range of fan speeds available, tolerance of airstream temperatures up to 200 degrees Fahrenheit, and easy motor accessibility. Motors for belt drive units are also generally lower cost and more readily available than those in direct drive vaneaxials. The four main design parameters for fans are power, flow rate, pressure rise, and efficiency. The calculation for these is done by considering a mean velocity triangle for flow only through an infinitesimal blade element. The blade is divided into many small elements, and various parameters are determined separately for each element. There are two theories that solve the parameters for axial fans: slipstream theory and blade element theory. In slipstream theory, the flow is assumed to be taking place in an imaginary converging duct where d equals the diameter of the propeller disc and ds equals diameter at the exit. In the top figure, the velocities c1 and c2 cannot change abruptly across the propeller disc, as that will create a shock wave, but the fan creates a pressure difference across the propeller disc, so c1 equals c2, but p1 does not equal p2. The thrust is given by the equation shown, and solving using the fluid equations Bernoulli's thrust difference in the continuity equation results in the following equation, which shows how the flow can be modeled where the diameter of the propeller disc and the diameter of the outlet are related. In blade element theory, a small element, dr, is taken at a distance r from the root of the blade, and all the forces acting on the element are analyzed to get a solution. In the figure, w is the mean velocity at a direction beta from the axial direction, delta L is the lift force perpendicular to w, and delta D is the drag force parallel to w. The axial and tangential forces are delta Fx and delta Fy respectively, and the resultant force, delta Fr, is at an angle phi to the lift. Resolving the forces in the figure result in the equation shown, which is how the thrust and torque can be found for an elemental section, as they are proportional to Fx and Fy respectively. Important characteristics of fans is the relationship between the pressure variation and the volume flow rate, which can be studied from the performance curves shown in the figure. A vertical line is drawn at the maximum efficiency point and intersects the pressure curve at the point S. It can be inferred from this that as the flow rate increases, the efficiency increases to a particular maximum, then decreases. The power output of the fan also increases with almost constant positive slope. Pressure fluctuations are also observed at low discharges, and at flow rates indicated by the point S, the pressure decreases. The pressure variations to the left of the point S causes unstable flow, which will be talked about next. The main causes of unstable flow in fans are stalling and surging, of which there are several types. These affect the fan's blades, performance, and output, making them undesirable. They can occur because of the physical properties of the fan, improper design, and are generally accompanied by noise generation. Stalling is caused by the separation of the flow from the blade surfaces. This effect can be explained by the flow over an airfoil, as shown in the figure. When the angle of incidence increases during the low velocity flow stage, at the entrance of the airfoil, the flow pattern changes and separation occurs. This is the first stage of stalling, and from this point, the flow separates, leading to the formation of backflow vortices in the separated region. The stall zone for the single axial fan and axial fans operating in parallel are shown in the top figure here. From the top figure, it can be inferred that the performance of fans in parallel is less than individual fans, and that fans should be operated in the safe zones to avoid the stalling effect. Because of this, axial fans with severe instability regions should not be operated at rotational speeds, blade angles, mass flow rates, and pressures that expose the fan to stall conditions. The other cause of unstable flow is surging, for which several criteria must be met. First, there must be a relatively large volume of air which is pressurized. There must be a section of ductwork with relatively high velocities, and the operating point of the system must be to the left of the peak pressure at lower flow rates. In this region, the fan curve has a positive slope such that increasing the flow also increases the fan static pressure. This results in insufficient air entering into the fan blades, causing separation of flow on the blade surface. This can cause complete breakdown in fans and is mainly attributed to three factors: system surge, fan surge, and paralleling. System surge occurs when the system resistance curve and static pressure curve of the fan intersect, have similar slopes, or are parallel to each other. Because of this, rather than intersecting at a definite point, the curves intersect over a certain region that reports system surge. These characteristics are not observed in axial fans, however. Fan surge results from the development of pressure gradients in the opposite direction of flow. This occurs when the blade rotation is insufficient to overcome pressure differences between the wheel center and discharge. Maximum pressure is observed at the discharge of the impeller blade, and minimum pressure is observed on the side opposite to the discharge. When the impeller blades are not rotating, these adverse pressure gradients pump the flow in the direction opposite to the direction of the fan. The result is the oscillation of the fan blades, creating vibrations and hence noise. Paralleling is an effect that is seen only with multiple fans, where the airflow capacities of the fans are compared and connected in the same outlet or same inlet conditions. This causes noise, specifically referred to as beating in the case of parallel fans. To avoid beating, fans are connected with differing inlet conditions, differences in rotational speeds, etc. Unstable flow can be avoided/reduced by designing the fan blades with proper hub-to-tip ratio and analyzing performance on the number of blades so that the flow doesn't separate on the blade surface. The hub-to-tip ratio of a fan is the ratio of the hub diameter to the blade tip diameter. Varying this ratio changes the fan's performance capabilities. Rotors with higher hub-to-tip ratios will generate higher static pressures, and rotors with lower hub-to-tip ratios will generate less static pressure. Selecting the correct hub-to-tip ratio for a given size fan can optimize fan efficiency and reduce chances of the fan stalling in the field if the system resistance increases. The guide vanes of the Vaneaxial fan also help avoid unstable flow by minimizing the swirl and straining the airflow, as mentioned earlier. Another method to overcome these effects is the recirculation of excess air through the fan. And since axial fans are highly specific speed devices, to operate them at high efficiency and to minimize the effects of unstable flow, they have to be operated at low speeds. For controlling and directing the flow, use of guide vanes is suggested, which is the main component of Vaneaxial fans. Lastly, turbulent flows at the inlet and outlet of fans cause stalling, so to prevent this, the flow should be made laminar by the introduction of a stator. Another way Vaneaxial fans improve efficiency is through static regain. Static regain is the conversion of kinetic energy or velocity pressure to potential energy or usable static pressure. Outlet cones, also known as diffuser sections, improve Vaneaxial efficiency by providing for static regain. This is important because Vaneaxial fans are typically high-volume air-moving devices with relatively high outlet velocities. These high outlet velocities and the resultant velocity pressures losses rob a Vaneaxial of a significant portion of its total efficiency. An outlet cone installed on the discharge end of a Vaneaxial fan allows high-velocity airflow to expand gradually, reducing velocity and converting much of the velocity pressure to usable static pressure. The energy-saving effect of this is apparent when two Vaneaxials with high outlet velocities are compared, one with an outlet cone and one without one. The fan selected with the outlet cone will require considerably less horsepower to deliver the same CFM and static pressure. An additional benefit is reduced duct resistance due to the lower duct velocity. Because of this, use of an outlet cone on a ducted or non-ducted Vaneaxial fan will reduce velocity pressure, allow static regain, and lower brake horsepower requirements. The long-term savings from the reduced electrical load will provide payback for the outlet cone in minimal time. This static regain makes Vaneaxial fans very desirable, and this combined with their minimal discharge vortex and straight-through airflow from the guide vanes results in efficiencies of 70 to 80% for fans with good operating points. And as seen in the figure, based on the velocity, it shows how much static pressure regain you can expect. Now there will be a quiz.